in the lecture today. A very full classroom. I know it's warm and slightly uncomfortable. But I'm going to have to ask, if you talk to your neighbor about the things in the class, please talk softly, because I've heard some feedback that some of the classrooms are very noisy. So if you talk to your neighbor, make sure you do it quite softly, and certainly if I can hear it. My hearing's not that good. Probably somebody else hears it. Okay. Oh, I did not change the year. 2012. Okay. It's a much changed lecture, actually. So today, we're going to do online learning, another type of supervised learning where the model is, well, there's really two models for online learning. One I hate to even call a model. One is a learning model. Online learning is very important nowadays. Why is it important? It's important as we have extremely large data sets now that are available to large companies. Maybe not available to individuals, but many of the algorithms we have require some form of optimization to find a solution. Online methods have a small memory footprint, and though they may take a long time to converge, they're at least, you can run them in memory. There's many versions of online learning, distributed online learning. Online learning as a method of optimizing your classifier or your predictor. Today, though, what I'm interested in is online learning as a learning model where in the normal supervised batch world, the model is we see a bunch of images and we forever learn our image of cat versus dog. We have our classifier, we predict on cat, we predict versus dog. We measure our performance in terms of how well we generalize on cats and dogs that we haven't seen, and we don't worry about updating our learner. And we're not going to, I don't think we will, go in so much into generalization bounds for this model this term, but many sorts of bounds proven for this model. Another model is the online model, whereas once more we have data, but the picture in our head is that our data is coming in sequentially. And it's not that we want to get a bunch of data, then build a predictor and find out our performance. That we see a data item, we want to make a prediction, measure how well we did on that prediction, then we see another data item, and we see another data item, and so forth, making a sequence of predictions, obtaining loss on every data item. So this division between training and test is obscured in online learning. It's a natural model. You can imagine that you want to do some form of investment. Well, every day you're going to maintain a portfolio. You put down your portfolio investments. You either change it, you receive some feedback on your portfolio. You don't care about building a portfolio that's good on future data. You want a strategy for adapting your portfolio constantly with changing data. And likewise, you can imagine if you're presenting advertisements online, so forth. Many things, data comes naturally online. Of course, we might actually be interested in a mix of models. Maybe we don't need to predict on every single data item we see. Maybe we train up our cat and dog, but we keep getting new data. Maybe there's no reason to not train up a new cat and dog classifier. Maybe we want some model that's a mix between them, but that's another story. Today we're going to focus on online learning. I have taken material all over the place for this lecture. A lot of thanks to you, Freud and Claudio Gentile, for a number of the slides. The better slides are theirs, the worst are mine. There's a book on online learning. There's other books, but this is a good one. Okay. Pragmatically, this is really to maybe you want a fast algorithm, maybe you want something to implement in memory. You don't want to have some form of statistical assumption to believe that your data works. Often good for large data sets. In terms of what we're going to prove today about the most basic online algorithms that there are, we're going to prove things with no statistical assumptions on the data. I.e., we don't draw our data IID from some distribution. IID isn't necessarily correspond to the world. We want to give bounds that are in some sense exact and not asymptotic. We're not concerned about performance in the limit, but we're concerned about performance what we see. I think today all we're going to really do is 3 models. We'll see the speed at which I lecture. For those of you who printed out older versions or looking at the one on the web, I have some stuff about graph-based learning. I've cut that from the lecture today. If we have time, maybe we'll look at an application. But I'm going to focus on learning with experts, learning with linear combination of experts. This is the Perceptron and Winnow algorithm, and learning with sequences of experts, where once more we'll assume that the data is strongly changing in that model. Okay. Okay, I'm going to play a game. Okay, so I don't know about you, but American football is on last night. I'm a big bettor. I like to bet on things, not to bet on horse races. Problem is I'm pretty ignorant. Basically I don't know what's going on. So I don't listen to my friends, because my friends don't know what's going on, but I listen to these experts who tell me how I should. Well, let's make it concrete. Let's make it a horse race, okay? We have this horse race, and there's these various experts who are telling you which horse to back or not, okay? So, and maybe we see a series of things over a number of days. Check out my own notes here. So on day 1, expert 1, for instance, says, bet this horse. Expert 2 also says, bet this horse. Expert 3 says, don't bet that horse. ... up to expert N, who doesn't say bet that horse. So this is the situation that I'll be faced with. I'll want to go ahead and listen to these experts in some way to make my own prediction. Maybe I'll listen to expert 3 and expert N and predict 0. And then perhaps the outcome then is 1. Very simple setup. So I made a mistake, so I incurred a loss. Maybe on day 2, similar situation. Experts 1 and experts 3 say bet this horse. Experts 2 and experts N say not. Maybe I go ahead and make my prediction. I call my prediction Y hat. I get the true label, and then perhaps I get it wrong again. Finally, day 3, I get it right. So I get a sequence of xt vectors in 0, 1 to n, where I can think of these vectors, if I want, as patterns. I can think of them as predictions from some given set of n experts. I then get some outcome in 0, 1 to the n, and I then get a label, and I then incur a loss. Okay.
Mark, excuse me, can you close your door, please?
Yes.
Thank you.
So, my goal is, if I'm making these bets, I'm spending my money, I want to minimize my online loss. And suppose I want to make a wild assumption, not a particularly reasonable assumption, but one we can later on. that one of these experts is going to be consistent with the data all the time. I.e., if we look at these experts, are any of them consistent with the data all the time? Expert 2 is always right, yes. Is there some strategy I can use to form my prediction from these experts' predictions so that I make minimal loss possible in the worst case? I.e., what do I mean by the worst case? By the worst case, I mean over any data set, which is trying to make me make mistakes, but is restricted to one expert always being correct. And I won't know which expert that is. I mean, it could be multiple experts being correct. How can I predict so that I make very little loss, and what can I limit my loss to? This is a question for you. What's some algorithm we could use, and what would that give us as a bound?
You give more weight to whichever expert is getting the most answers right until that moment.
That definitely sounds like what a good algorithm should do. And so what sort of, can we use that idea to come up with an algorithm and somehow put a guarantee, an upper bound, say that we'll make no more than some given amount of mistakes? How should we play this game?
Well, each iteration you can throw away everyone who made a mistake.
Okay.
Any expert that didn't get it right,
Yes.
you can discard them. So you're left with ones at each time who've been correct all the time so far.
Okay, so that's great. So if we do just that, if we just throw away people who make a mistake, you know that, say we predict with somebody at random and that person's correct, we're fine. If they make a mistake or anybody else makes a mistake, we'll throw them away. At each trial, we'll throw away at least one expert, so we'll make no more than n-1 mistakes if there exists some consistent expert.
Yeah.
Yeah.
Just throw them all away.
What?
You would throw them all away.
Well, we're assuming that there's a consistent expert. So the consistent expert never will make a mistake. So we'll never throw away the consistent expert. So that gives us an upper bound of n-1 mistakes. But being a machine learning course, we're greedy. We want to do better than that. We want to improve exponentially on that. How can we go ahead and improve exponentially on that? So we can get a bound of n-1 by just throwing away people who are wrong, but we can do far better. How do we predict so that we guarantee that we do far better than n-1? I.e., consistent strategy gives us n-1.
Throw more than one of them?
Throw away more than one of them. Yes, I agree with you. So how should we predict so that if we make a mistake, we're always guaranteed to throw away a lot of them?
So you can throw away half, or halve in some sense, but I can't see how you make sure, you don't know if the ones you're keeping are going to continue to be consistent or not.
Correct. You have the right idea. Does somebody want to elaborate on the argument that's just been begun?
Can I ask something?
Please.
Do we know that there is
We're given
well,
the
with-
assumption there's at least one consistent.
At
There
least
might
one
be
consistent.
20 consistent. There might be
He's consistent 100% of the time.
yes, consistently correct 100% of the time.
Sorry, if we know that there is one consistent, why don't we just drop all the inconsistent ones?
Okay, so let's say every trial we drop every consistent one, inconsistent one. The problem is maybe every trial there's only one person who's inconsistent, and so we drop only one
In the worst
inconsistent.
case.
Yeah, in the worst case.
Okay.
So we want to give an analysis that takes that into account.
Sorry.
Yes.
Actually, that's not the upper boundary as far as I can see, because if we have one that's going to be consistently correct, it doesn't say that the others cannot be consistently correct over the length of our test run.
Yes. The others.
So we
could
wouldn't
be-
have anyone to throw out.
Right. So it might take more trials, but let's say we're choosing a prediction at one of the experts at random, okay? We'll only make a mistake if we've chosen an expert of somebody that's wrong. Okay, so you are correct. We may take an infinite amount of time to throw out all the experts, but we'll still only make n-1 mistakes if we always predict with somebody who's consistent, because up to that point in time.
Okay.
Because we'll always cross out at least one person per trial. We want to somehow guarantee we can cross out a bunch of people whenever we make a mistake. You know, on trials where everybody predicts right, obviously we're not going to cross anybody out. So we can't guarantee on a trial that we're going to cross anybody out. We can only guarantee to cross out people when we make a mistake.
So now we're playing an infinite game, Bill.
It could go on an arbitrary amount of time. You know, it's fine. It's like playing the market. You know, you want to make money as much as we're not.
I don't know anyone who played the market infinitely long, but I believe it.
Yeah, but the point is to minimize mistakes or to maximize loss. It's not. The goal isn't. You know, we want to minimize mistakes, and we're saying that the game is potentially unbounded. I mean, if you want to put a bound on the top of the game, then it doesn't change anything. All it says is, well, the number of mistakes we'll make is bounded by this or the however long we play the game.
Just I'm a bit disappointed. I was hoping for a recipe for winning some amount of money with horse bets, and now I find out that I have to go to the racetrack like forever for your strategy to work.
You know, I live in happy math world. In happy math world, you can go to the racetrack forever and win arbitrary amounts of money and spend it on arbitrarily large steak dinners, and it doesn't kill any animals, and you can feel happy.
Fair enough.
I'm not going to teach you how to make a lot of money.
If you're more concerned about losing, then you can just throw away half every time. So the worst case is you'll end up in log n. You'll end up.
So
you'll
how
end
can
up
you
throwing
guarantee
people away.
that you'll throw away half every time?
You're taking the risk that you'll throw away people who have been consistently correct to date. But the
Well,
worst
that's
case-
not good then.
No, that's right. So if you're more concerned about cutting your losses early, then if it terminates after so many steps, then whoever's left is consistent. But
You're
if
saying
trying-
you're just going to throw away half, whether they're predicted right or wrong, no matter what.
you prioritize throwing away the guys that make it, who get it wrong.
We can do better. We don't need to do this. I don't understand. Yes.
Venture, I guess. I mean, at our first go, I guess you're none the wiser. Just predict one or the other.
Okay.
And then you get those people who got it right,
Yes.
and you predict, and then you look at their next prediction,
Yeah.
and you predict opposite.
No, we're going to do something simpler. Yes.
Would it be real stupid to throw out the half and go with the first half we kept, and then if they make a mistake, take the other half back and go with that and half it again.
I think you're getting the idea about having things
Why are we
correct.
halving them?
That's how you get exponential.
Because if you somehow we have things, we go from linear to exponential. Yes.
Why do we have to throw the expert? So instead we should pick the one who has the maximum score every time.
Yes.
So when somebody says somebody is not right.
The problem is there's going to be a lot of people who are tied at maximum score. Everybody.
In that case, you pick one of them. And so each case, you still have maintain the pool of experts and pick the best of them.
Okay. So how can we do this to improve on n-1? We're looking to improve on n-1 in the worst case.
The halving part will improve it by half.
Okay, so let me clarify in case it isn't clear how we can have so it's like what we're going to do. Our prediction strategy will be like it's the elections coming up in the U.S. Majority rule, not really majority in elections. But what we're going to do is on every trial, we're going to simply predict with the majority of consistent experts. Okay? The majority of consistent experts is at least 50% of the consistent experts. If we get it right, we're happy. We didn't lose any money. Okay? If we got it wrong, well, we're unhappy. We lost money, but we've gotten rid of at least 50% of the people who are consistent so far. Next trial, same story again. Every time, imagine our experts consist of a bunch of area. If we don't make a mistake, as far as our analysis is concerned, nothing happens. If we make a mistake, we've gotten rid of, well, maybe we've gotten rid of slightly more than 50%, but we always get rid of at a minimum of 50% if we predict the majority. How many times can we eliminate 50% from a finite set of n items? Log 2 n times. Okay, so this is a halving algorithm. Many names for it. Very, sometimes called a version space algorithm. Very influential in machine learning. Okay. So here you can see an example. Here we have the 8 experts. Well, I guess the majority is equal. Maybe we flip a coin and predict 1. The true label was 0. We eliminate all those people who made a mistake. That was E1, E2, E5, E6. Then the next trial, we see 3, E4, E7, E8 are the majority. We predict with the majority. So we keep, we don't count anything in our analysis. We still have 3 experts, and so forth. So every time we make a mistake, we eliminate at least 50%. So we can get no more than log 2 n mistakes. Okay, questions on how this argument works? Of course, we started out with an unrealistic assumption. The assumption that we started out with was that we had a consistent expert. So what might you do if you don't have a consistent expert? How might you fix things up? Well, you can imagine that, if you don't have a consistent expert, I guess there's a number of things you could do, but one thing which works nicely is you somehow weight the experts based on how well they're doing. You weight them in terms of their relative correctness, and you have some sort of voting. So what we're going to be after is the following then, which we're going to say we have a sequence of examples. We'll say LAS will be the loss of our algorithm, which is our master algorithm. Li will be the loss of the ith expert. And so previously, when we had no loss, we proved a bound of log 2n. Now we want to perhaps say, well, it might be hard to do better than the best expert. So we'll try to do not much worse than the best expert, plus some form of regret for not knowing who that best expert is, which we'll say is log n. Okay? It's a nice technique for algorithm design. Suppose you don't know whether to use a neural network or an SVM. Suppose you don't know what kernel you should use, what parameters you should use. Well, what you can do is run with, as long as you have the computational power, thousands, hundreds of thousands of them. And the online loss will do not much worse than the best, which is this term, plus, you know, a million, log of a million is only like 8 or 10. You know, I don't know, it grows quite slowly. So it suggests that if we can prove a bound of this form, a nice approach to learning is to mix in a lot of algorithms if you have the computational power to do so. Okay.
And what's the experts?
N is the number of experts, yes. N for us will be the number of experts. Okay. Classic algorithm to do this is the weighted majority algorithm. So now, because we're not assuming somebody is consistent, instead what we'll do is we'll vote, each expert will have a weight, we'll vote with their weight, and when they make a mistake, we'll multiply their weight by some factor beta. Okay? So in the case where we assume that there's a consistent expert, that's like assuming beta is 0. And in the case where things are very noisy, perhaps we'd want to choose a beta near 1, i.e. somebody makes a mistake on the trial, we're not too confident about what that means. Okay? Okay, let's go ahead and analyze this proposed algorithm. Questions so far? Okay, let's introduce notation. MTI will be the number of mistakes of expert I before trial T, at the beginning of trial T. We'll weight each expert, so it's this beta to the number of mistakes they made. So their weight goes exponentially down with the number of mistakes they make. And then we'll use WT as the total weight, the trial T. So the prediction, just to remind ourselves, what we're going to do is we keep track of those weights, and we're going to simply sum up the people who predict 0, sum up the people who predict 1, see who has the larger weight. Okay. Okay, so we want to bound what happens with this algorithm, whether we make a mistake. Well, so on the trials where we don't make a mistake, maybe we'll punish the minority. We don't have to, but on if no mistake was made, that meant the majority dominated the pool. And that means that we could certainly bound the total weight at the end of the trial by the initial weight, because we only decrease weights. So we're going to give every expert a weight of 1, and we're going to punish them by beta if they make a mistake. What happens on trials where we make a mistake now? In the other case, we simply wiped out at least 50% of the weight, okay? And so if we set beta equal to 0, we could see that we'd be wiping out at least 50% of the weight. But now, we're in a softer, kinder future where we're tolerating experts who make errors. Okay. So the minority, the people who got it correct, in the case when there's no mistake, their weight's unchanged. The majority gets reduced by beta over 2. So WT plus 1 is less than 1 plus beta over 2 when we make a mistake. Questions where these inequalities come. So I'm going to put these inequalities together to make a bound in a moment. Okay, so where does this first equation come from then? How did I get this?
Reiterate the previous formula.
Yeah, so the number of times, I'm just counting the number of times I made a mistake. If it goes down, if it doesn't go down at all on the trials I don't make a mistake, I don't worry, but the trials I make a mistake, it goes down at least by 1 plus beta over 2. And so that happens m times. So that gives me an upper bound on this weight. Now in this next line, I'm proving a lower bound on this weight in terms of an individual expert, i.e. all the weight in the pool is lower bounded by the weight of any particular expert in the pool. What's the weight of an expert in a pool? It's just beta times the number of mistakes I have. So I have this upper and lower bound on WT plus 1. I have the final weight, I'll call it W fin. W fin is bounded below by beta to mi, where mi is any expert. And it's upper bounded by 1 plus beta to the 2 by m, where m is the mistakes in the master algorithm. Okay, so with these two bounds, I can now go ahead. Maybe I make mistakes at algebra constantly, so it's a risk if I try to do this inequality myself. But go ahead and we take we have W1, the initial weight. Okay, so let's take logs here. So we have m times log of 1 plus beta divided by 2 plus the weight of W1. If each expert has a weight of 1, that's the log of n. And we have that's greater than or equal to mi times the log of beta. Let's go ahead and rearrange and divide. So I'll put m here. I'll put that here. Mi, I'll move the log n to the other side. So I have mi times log beta minus log n. If I divide both sides, I move this over here, I divide both sides by log 1 plus beta over 2, that's a negative number. Dividing both sides of an inequality by a negative number, I have log 1 plus beta over 2. Now if I multiply top and bottom by negative 1, I get exactly that. So now if I multiply this by negative 1, and that by negative 1, have the form there after I separate the denominator. Okay.
What's your W fin? Yeah?
W fin is on the previous slide, but the total final weight, the weight at the very end. So the weight at the very end of playing this game is lower bounded by the weight of any individual expert, i.e. any individual expert has weight beta times mi, just the number of mistakes it had if its initial weight was 1. The total weight in the pool, W1 is n, that's capital N because everybody starts with a weight of 1. Okay? And so I just started doing the algebra. I could go into more steps, but the more steps I do, the higher the probability is that I'll make a mistake. But if something's unclear, let me know. But here, -1, so this becomes a plus, this becomes a log 1 over beta. -1, this becomes a log 2 over 1 plus beta. And if you look on the next slide, that corresponds to the terms. So now there's all sorts of stories that you might want to tell about how to choose beta. But because we're keeping this lecture simple, you can imagine choosing beta adaptively in some fashion. I just want a bound that looks simple, okay? And so for a bound that looks simple, and with an arbitrary choice of beta of 1 over e, I get roughly 2.6 times loss of the best expert times 2.6 times log n is the performance of this algorithm. So I'll do a bit under a factor of 3 times loss of the best plus another term 3 times log n. Much of work in these type of areas is involved in getting that a term to a 1, and because you somehow can't do better than the best, but you can hope to kind of get close to the best. But right now I'm not worried about this detail of trying to get a down to 1. Questions? So the setup I showed you is very simple, counting mistakes. This is a heavily studied area, lots of results here, but you can generalize it over much larger setups. So we might want to have values in R, we might want to have an absolute loss function, we might want to have square loss, many possible losses. A very simple algorithm you can use, there's improved algorithms, is you can predict with the normalized, now, since you want to predict a smooth value, not just predict 1 or 0, you can imagine that you predict with the dot product. So rather than predicting outcome 1 or outcome 0, maybe you predict 0.25, and maybe your feedback is 0.5. So the natural thing to do is to generalize this to the dot product here. It turns out that counting mistakes is actually kind of a hard framework. It's much easier, unsurprisingly, to do things with the square loss. If we change the setup to the square loss, and where our instances are in 0 to 1 and our outcomes are in 0 to 1, and we predict with the dot product, well, it turns out we do as well as the best plus something that looks like 2 times log n. With a more sophisticated algorithm, you can get it down to 1/2 log n. This proof of 2 times log n isn't bad, but I don't want to do too many proofs. It has the same flavor as what we've just done, but you have to generalize it a bit more. Okay. When you have the discrete loss and absolute loss, somehow you always get something more than 1 there.
Sorry,
yes.
how do you quantify the degree of functionalness?
Yes, okay, let me explain what these 2 columns are, okay? We want to generalize to the case where you have smooth prediction. So a very simple way of predicting is with the dot product, and that gives you a bound. There's something that you can do that's actually slightly better than the dot product in this framework. Because it's more complicated than the dot product, which is simple. I'm calling it fancy. There's no degree of fanciness. Okay, it's just a phrase. It's fancy with respect to the dot product. The dot product is simple.
How do you derive these numbers, 1, 1/2, and
You have to. It comes from the proof. I didn't. I didn't prove it for the dot product. I'm not proving it for fancy. I can go ahead. I'm not going to ask you to memorize these numbers, but if you forced me, I could do the proof. I don't know if I can do it off the top of my head, but I can show you the flavor of the proof, how it works at least. Okay. And these are kind of they're tight in some sense. The fancy ones are tight in the sense that there exist sequences. This one is always tight. You can somehow never do better than the best. In the worst case, this other term may or may not be tight, but you can force sequences so you approach these numbers for the additional term. Other questions? In terms of what I'm interested in you understanding, I'm interested in you understanding how, I'm just showing that you can generalize from counting mistakes. And I've shown you the proof and how to give the bound for counting mistakes. And with a bit more work, you can generalize, but I'm not going to ask you to look into the details of how you generalize it unless you're interested. Okay. So the observation is, I said before, is you have this suggests an algorithm design approach. If you want to build an algorithm for a problem, well, why don't you use a lot of algorithms and mix your prediction from all those algorithms, whether it's with a dot product in that case, in one case, or a majority vote in the other case, because you're guaranteed to do almost as well as the best, and you'll only do logarithmically in the number of algorithms you've mixed. Okay, these are all. Okay, so what we're going to next do is we're going to generalize to a case that you're more familiar with from SVMs and the rest of the course, where we're going to look at linear combination of experts. So we're going to do that with the perceptron and the Lino algorithm. But we're not going to perhaps address these more abstract questions about why did we update by multiplying the weight rather than some other monotonic scoring thing on how the person's performed. This is a question you might want to ask yourself: why multiply the weight? Why not do something else? We got a good bound that was good enough for us for now. Okay. I should note, I'll get a final version of slides on the net, but there's some difference on the handouts from the slides that I'm using. So more generally, our sequence, our setting is now the following. We're given a sequence of instances xt, where you can imagine, for instance, they're in Rn. We're going to make some prediction of our trial. We're going to receive a label, and then we're going to incur a loss, and that'll be the total loss of our algorithm. We'll denote S as a sequence of examples. U will correspond to some hypothesis space, some comparison class of predictors like linear functions, polynomials, a general guarantee that people are interested in is people like bounds that say that your algorithm, the loss of your algorithm's not much worse than the loss of the best thing in your comparison class of algorithms bounded by some amount. So we did this where our comparisons were just n discrete experts. Because the proofs start to get quite technical, I'm not going to do this for linear threshold functions. Instead, I'm going to assume, like we did with the consistent experts, that there's always some consistent linear threshold function for our data. Everything, just like we generalize from the halving to the experts algorithm, we can generalize these other algorithms in natural ways to the inconsistent case, but it adds a lot of technicalities to the proofs. questions? And actually, because it's going to make for an interesting comparison to understand what's going on, not going to work directly. For the perceptron, we'll prove a bound for linear threshold functions, but we're going to compare the perceptron with the Winnow algorithm in a different setup. So today, we're going to think about learning Boolean functions. So you're with graphs last night you had a discrete function, but previously in the course you've been interested in perhaps learning smooth functions. But we can also imagine learning Boolean functions. We have some function which can somehow corresponds to some logic thing on the attributes. I'll give an example of what I mean in a moment. But first, some notation from learning Boolean functions. We can represent Boolean functions as a map from 0, 1 to the n into 0, 1, or minus 1, or 1 to the n. We're going to represent things both ways today because it's going to make our life slightly easier. One algorithm is easier to look at as a map from 0, 1 to 0, 1. The other algorithm is going to be easier to look at as a map from minus 1, 1 to 1. What are our basic Boolean functions? We can have x1 and x2. So that's of course true if both x1 and x2 are true. It's false if either of them are false. So in our setup for today, then we have x1 and x2, and we have x1, x2. And 0, 0, 0, 1, 1, 0, 1, 1. And they're both false. 0 will be false. This will be false. If one of them is false, it will be false if both are true. Likewise, we could do this with negative ones. In the negative ones case, false, false. 1, 1, negative 1. 1, negative 1, negative 1, and 1, 1, 1. So these are, either we're going to be using 0, 0 for false and 1 for true, or we'll be using 1 for true and negative 1 for false. If it's in zeros, or so it's 1, 2, and 3, we can represent in Boolean x1 and x2 as x1 times x2, x1 or x2 as x1 plus x2, round to 0 or 1. Not, we can do 1 minus x1. Okay. Notation, a single variable is called a literal, so like x1 or x5 negated is known as a literal. A term is a conjunction of literals, i.e. so if x1 is true and x3 is true, that's an example of a term. Not x4, x5, x7 is only true when all three of these are true, i.e. when x4 is false and x5 and x7 is false. This is a term. A clause is a disjunction of literals. That's a set of ors connecting the literals. Because things are going to be simpler, we're going to forget about negation pretty much today. Monotone disjunction or conjunction, no negated literals. Okay, so the comparison class of all possible terms or conjunctions will denote with this U. The set of all possible conjunctions will denote with this U. So for instance, how many possible disjunctions are there over how many, let's say, how many possible monotone disjunctions are there over n variables? So it's just a matter of, we have 2 to that, and then somebody said, it's just a matter either with each, given any n variables, any k of those n variables, we can make a clause out of them. So there's some 2 to the n possible different disjunctions, and likewise for conjunctions. Okay. So with the SVM, and you've seen, you're used to the idea of learning a linear function and using it as a classifier. I should have written my b inside the parentheses, I can see, so that's a typo in the first place. But so we can write some linear threshold function as u dot x plus b. So it's those functions determined by the separating hyperplane.
Sorry, but
Yes.
the previous slide,
Yes.
the cardinality of the U sets,
Yes.
did you say it's 2 to the power of n?
Correct.
Isn't it anti-factorial?
No.
No?
Because.
It's the, okay, sorry.
Okay.
Okay. Whatever.
Other questions so far? Okay. Okay, so the set of all linear threshold functions, which if I corresponds to a set of Boolean functions, is determined, we'll call ULT. Just to point out what we would need to do, if we want to have non-monotone disjunctions, the easiest way to incorporate that is to introduce a feature map, whereas for each variable we also include the negative of the variable. And that way, observe that over this feature map, we can now include negative non-monotone disjunctions, because in the feature map, it's now monotonic. It's monotonic in the negative variable, negative of the variable. Okay.
But yeah, can you read the transparent feature map? What's the purpose of it?
So we're going to have algorithms which it's easy to analyze in terms of a monotone disjunction. Okay. But suppose we wanted to learn a non-monotone disjunction with a algorithm that learns monotone disjunctions. It's just like what you did with kernel functions. You have a function that learns a linear function, and you want to learn a polynomial function. And so, suppose I have an instance. Suppose I have that, I have some logic. Maybe I have 3 variables: x1, x2, x3, and the disjunction is x1 or not x2, and I want to learn that. Okay. So the feature map that we're proposing is the following: is let's just put some random things down. So maybe this is a -1. This is a -1. This is -1. The feature map which I'm proposing is we simply double the number of features by x. So this will go to 1, -1, -1, 1, 1, minus 1. We include each element plus its negation. That way, if we're trying to learn negative x2, it's like learning a disjunction over the negated variable. Questions how that works? Okay, maybe this is a good place to take a break for 10 minutes.